Alright, so I've graphed both of these equations that were in that problem involving New York City and Los Angeles populations. The problem is these numbers are so huge that the original window will not show what you need to see. So we can zoom out manually, or like by hand, if we move the cursor, the mouse cursor, over to the x-axis. The cursor will turn into a little hand that looks like it's trying to grab something. You can click and hold. The hand will close. And then you can move the hand around and it will zoom out. Or you can move it back the other way and it will zoom back in. Okay? But if I zoom in, like as far as I can go, all that's going to happen is I'm going to see these two lines kind of turn into basically the x-axis. Okay? They look like vertical lines, but we know that they're not. The reason they look so vertical is why? Yeah, because the slope is so steep. We're talking about 251,000 over 1. So it goes up 251,000 before it even goes over 1 unit to the right. So no matter what I do, this is going to just look like vertical lines if I zoom out like this. So what I need to do is change the settings of the window manually so that the scale, basically what I'm doing is forcing the calculator into a scale that I want it to have. Okay? Now, I'm never going to have a negative population and I'm never going to have a negative time. So that means I don't need those negative values that are on my graph. That'll save me some space. So I'm going to press menu to do this by hand, manually, change this over manually. And I want window zoom. The window is the viewing window. And I'm just going to go to Windows Settings. So there's all these settings that I can use here, but I want to go to Windows Settings because I want to make these changes by hand. Once I do that, it brings up my X minimum, which would be the smallest value on my X-axis that the calculator will show. X max, the biggest value on the X-axis. Y min, the smallest value on the Y-axis that the calculator will show, and so on. Okay? We don't have to worry about scale. It will take care of that automatically for us. What is the smallest number of X that I need on my graph? 0, because we don't have a negative population. We don't have negative time. Now, on the X-axis, what is the biggest number that I need? Think about what we're talking about here. What would be on the X-axis? We have years in population, right? So years. How many years am I talking about here? Is it 10 years? What is it? There's 50 years listed, right? On our calculators, we entered in 50 years for that last population. So why don't we make that something more than 50? Because we know that these populations are not the same yet. They will cross, but they will cross sometime in the future. So let's make that 100. That'll take us out to 2050. And maybe they'll cross then. What is the smallest Y value that I need here? 0 again, because I don't have a population that's negative. So I'm going to delete all that stuff and have a population of 0 for a minimum. Now the max population, this is where it gets tricky. We have y-intercepts that are in the millions already. We have populations that are in the millions. So we need to look at the biggest population in our graph and then let that population get even bigger. So what's the biggest population that we have on our data? And both of these populations are growing. So we know we need 21 million. And as time goes on, we're going to need more than 21 million. Okay? So, I don't know, maybe 50 million? What do you think? Is that going to be enough maybe? All right. So let's try 50 million. So think about it as you do it. 50, and then 1, 2, 3, 4, 5, 6 gives me 50 million. Now, let's try that and see. We should see two lines that cross. If we don't, then we need to change our scale again. So I'm just going to hit enter, and look at that. I have two lines that cross. And they're not vertical lines. Okay? So changing the scale really helped. So now what I need to do is find where these two lines cross. And I'm not going to do that by hand. That's ridiculous. I'm doing this on a calculator. I want the calculator to do it for me. Anytime I want the calculator to do something for me, I'm going to press what button? Menu. And then I'm going to do what? Analyze. Like I said, anytime you want something to happen here, you're choosing Analyze. Now, of these options, which one do we probably want? Intersection. So that's number 4. And now it's going to ask me lower bound. If you notice in the lower left-hand corner it says lower bound, that means get on the lower x value side of the intersection point. So that means be on the left side of your intersection. Once you're on the left side of your intersection, go ahead and click. And that lower bound will change to upper bound. Now you just slide across, capturing that intersection point, and it will give you an ordered pair and a dot where it thinks the intersection is. So go ahead and click once you have that to get out of the operation we're trying to do here. And now if you notice on my window it says 86.9, comma, and then I don't see anything. So what I'm going to do now is click and hold on that. I'm going to move my mouse over here so I see the little grippy hand. Click and hold. It will grab that ordered pair, and then I can move it anywhere I want so that I can actually see what it's saying. So now that says 86.9, comma, 2.56 e plus 7. And we talked about what that e plus 7 means, right? That's scientific notation. So when we write that down, we're going to write 256 and then 5 zeros after it. Okay? So we need to write that down on our notes. 86.9, comma, 2.56 e plus 7. So go back to the notes. And I need my pen. What was my ordered pair? $86.9, comma, was it 2.56? So 256, but it was times 10 to the 7th. So that decimal was there. I move it over 1, 2, 3, 4, 5, 6, 7. So the question is, what do these two coordinates represent? Good. This is years, and this is population. So now we can answer the question because we have this ordered pair sitting here. The question says, assuming these linear trends continue, when will the populations of these regions be equal, and what will that population be? So to answer the question completely, we know it's 86.9 years, but that doesn't answer the question. To answer the question, I have to go back and say, oh yeah, that was 1950. So this is actually 86.9 years since 1950. What year will that be? 2036.9 is my year. So basically almost 2037. And the population then will be 25,600,000 people. So I can write year 2036.9, population 25,600,000 people. The populations of New York and Los Angeles will be the same, according to this data. Same exact idea on this problem. The table shows the populations of San Diego and Detroit. Assuming the trends continue, when will the populations of these regions be equal, and what will that population be? So before I set you guys loose on this problem, let's take a look at the population of San Diego. How is it changing? It's growing. And take a look at the population of Detroit. How is it changing? It's decreasing. Okay? And this is actually legitimate. Detroit used to be a very, very powerful city, and now they don't even have 1 million people anymore. And this number right here is actually way less now. These days, I don't even know if they're over 700,000 people. People are leaving the city like crazy. People are leaving the state of Michigan like crazy. I'm one of them. So San Diego has a graph that's going like this. Detroit has a graph that's going like this. What are we looking for? We're looking for the intersection. That will give me the year that the populations will be the same. Maybe it's already happened. I don't know. and also the population that they will have. Okay? Problem is done exactly the same way. Go ahead. Just so that we all see it one more time, I've entered all of the data in from that table. I called the first column year, the second column I called SD for San Diego, and the third column I tried to call DET for Detroit, and it gave me an error because DET is already defined, so I had to actually type out the whole word Detroit. Instead of writing 1950, 1960, I'm going with 0 is 1950. That makes my numbers simpler. And then I've entered in all of the data there. So from here, I go home, and I want to insert a new document. But actually, I've already done that, so I'm not going to do that. I'm going to go back here and press Control to the right, and that gives me my scatter plot for Detroit. Now, the population is decreasing for Detroit, so I should see that downward trend, right? Yeah? Which means my slope in this case should be negative. Okay? So, menu, analyze, regression, which is option 6, and then slope-intercept form. There's my equation, and I did wind up with a negative sign. If you can't read that, like I'm kind of having trouble reading that over that dot, again, you can move your mouse over, click and hold until it grabs it, and then I'm just going to slide that up there so that I can actually read the equation. Then I'll write that equation down. That's the equation for Detroit. Now I don't need to make a brand new scatter plot here. I don't have to do anything except for to come up with San Diego, I do what? Yeah, just move over to the y-axis, click on Detroit, which is funny because that's actually a slogan that they have, clickondetroit.com. And I'm going to slide down to San Diego. Click on that one, and my scatter plot changes automatically, so does the equation, and I can write that one down. That one I can actually read. So once you have these two equations written down, what do you do? Yep, we're going to go home, and now I'm going to go down to the second icon from the left, add a graph to my document. There's my graph, and now it's listed up in the tabs. It's 1.3. My scatter plot is 1.2. I can press Control left to get back to it. My data that I entered in is 1.1. I can press Control left to get back to that. And if I want to go back to my other graphs, I can just Control left and right all the way back through. So now we enter those two equations in, and then we're probably going to have to change the scale here because, again, we're talking about millions of people. Okay? So if you're at that point, go ahead and continue. So these are the two equations that we have. Before I show you the graph, I want to talk about what these mean. What does this slope right here on the San Diego equation tell me about San Diego? What about it? Yeah, but so the population is growing by 17,816.6 people per year. What does this slope tell me about Detroit? The population is decreasing at a rate of, so they're losing 19,217.6 people per year. What does this number right here tell me? I'm in slope-intercept form. What is this number? It's the y-intercept, so what does that tell me? According to my equation, in the year, what, if I'm talking about the y-intercept? Year 0, according to our equation, but according to the actual problem, year 1950, according to our equation, the population of San Diego was 356,896. Is that true? No. We know that the population in 1950 of San Diego was 334,387. But we are generating a line of best fit, and that's why our y-intercept does not match the data that we're given. Okay? Same thing is true for Detroit. In 1950, the population of Detroit was 1,849,400. Well, the population of Detroit here actually is pretty close, isn't it? So for the y-intercept here in Detroit, we are looking pretty good. It's pretty accurate. But this is different than this because we are working with a trend line not with the actual data anymore. All right, so we enter that stuff into our graphs, and let me go back to my calculator here. I have entered the lines in already. This got moved somehow, so let me move it back. There we go. And I'm just going to zoom out now. The graphs are entered. So I press menu. I don't press that button. Go back to my graph. So there we go. Unsaved document. There we go. Menu. And I want to change the window. Window settings. I don't need a negative amount of years. But I do need lots of years. How many years do I need here? Maybe 100? Actually, if you look at the problem, the populations have already crossed. I don't need 100. I just need 50. That's fine. If you put 100 in, it's no big deal. The goal is just to get the intersection point on the window so that you can find it. Y minimum, I don't need negative numbers. Y maximum, I'm dealing with big populations, right? But they're not over 2 million, so I'm just going to put in 2 million. Let's see, that's 20,000, 200,000, 2 million. There we go. Press enter, and there's my intersection. So now, we press menu, and we want to do something, so we're going to press analyze, and we're going to find the, what? Intersection, so that's option 4. It says lower bound, so as long as I'm on the left side, the lower x values, I'm good, so I can click, and then I just slide across until it gives me my intersection. It did, so now I can click out of that. There is the intersection. Of course, I can't read it, so I'm going to click and grab it. There we go, and slide it over here so I can actually read that thing. It is 40.3 years since 1950, and 1.07 times 10 to the 6th power population. So now I go back to my notes, and I can write that down. We get the ordered pair 40.3, comma, 1,107,000. I can move the decimal over 6 places. 1, 2, 3, 4, 5, 6, comma, comma. So, what does that 40.3 represent again? Years since 1950. So that actually is going to be what year? 1990.3. So 3/10 of the way through 1990. And the 1,070,000 was the population. And that is actually really true. That's what happened. Now that we've learned how to graph systems to find solutions, or use tables for systems to find solutions, or use a calculator to graph to find your solutions, we can talk about what these systems are that we're dealing with. All systems are either consistent or inconsistent, and somebody used these vocab words already to describe a system. All consistent systems are either independent or dependent. Okay? So either you are consistent or inconsistent. If you are consistent, then you are either independent or dependent. We've got to learn what those words mean. Consistent systems have a solution. Inconsistent systems, no solution. If it has a solution, that means the lines cross. If it doesn't have a solution, that means lines don't cross, which would mean they're parallel if they're lines. Okay, for consistent systems, if you are dependent, then both lines are exactly the same. If I were to draw a little graph of that, then my red line is my first line, and my green line is my second line, and my green line is exactly the same line as my first line. You would see exactly the same equation for those two lines. That means they're dependent. And the other thing I want to say there is there's an infinite, so infinitely many solutions. Because every ordered pair for both lines works for both equations every time. That's why there's an infinitely many number of solutions. For independent, if I were to draw a graph here, and I had my red line and my green line, so here's my red line this time, and this time my green line looks like this. What happens for an independent situation is lines cross exactly once. There's one ordered pair that works. So therefore you have exactly one solution. The little note over here to classify a system without graphing, you don't have to graph these. All you have to do is look at the slope and y-intercept of each. If you put your equations in slope-intercept form, if they have the same slope, then they are either parallel, meaning that there is no solution, or if you look at the y-intercepts and see that they are exactly the same y-intercept as well, then they are exactly the same line, and therefore you have infinitely many solutions. If you put your lines in slope-intercept form and they do not have the same slope, then automatically you have two lines that will cross exactly once, and therefore you will have one solution. So that's how you can do problems that are asking you to classify systems. Put them in slope-intercept form first. Then look at the slopes. Are they different? Fine. It's an independent system. Are they the same? Well, then you might have a dependent system or an inconsistent system. Look at the y-intercepts then. So, here we go. Classify each system as independent, dependent, or inconsistent without graphing. So put these in slope-intercept form. This top one right here, all I have to do is add 3x to both sides. So I get y equals 3x plus 4. The bottom one I got to do a little bit more work. I subtract x from both sides, and now I have negative 1/3 y equals negative x plus 1. I need to get y by itself, though, so that means I'm going to multiply both sides times what? Negative 3. So now I have positive y equals positive 3x minus 3. All right, my two equations are in slope-intercept form. Look at the slopes. What are they? Same or different? They are the same slope. So that means I'm either talking about infinitely many solutions or no solution. Look at the y-intercepts. I have the same slope, but I have different y-intercepts, which means that these lines are, if I graph them, they are parallel. They're parallel. These are parallel lines, yeah. So this is a inconsistent system of equations. And therefore, it doesn't ask me to do so, but how many solutions do I have? If it's inconsistent, they're parallel lines, they don't cross, there is no solution. So for the second one, I put this in slope-intercept form. I move the 2x over, and now I have negative 2x plus 1, divide both sides by 3. So I get y equals negative 2/3 x plus 1/2. 1/3, sorry. My second one, all I got to do is subtract 4x from both sides, and I get y equals negative 4x minus 3. Look at the two slopes. They're totally different, which means that this is consistent, independent. They cross, which means there is exactly one solution. Finally, for the last one, already in slope-intercept form here, I subtract 6x from both sides, so now I have negative 3y equals negative 6x plus 9. Divide both sides by negative 3, and I have y equals positive 2x minus 3. Compare the two slopes. They are the same. Compare the y-intercepts. They're different. So these two lines, if I were to graph them, are actually parallel, which means I have inconsistent again, which means there's no solution. That's the section. So let's do next time.